In this lesson, we'll talk about something called optimization. And if you have something that is optimal, it means the best or the desired case. And that could be a maximum value or a minimum value. That's what we usually look for. So in this case, if we have 100 feet of fence to make a rectangular pen against a wall, we could just put the fence against the wall and there would be zero area. That would be the minimum area, but here we want the greatest area. We want to maximize the area of the rectangle, and so that's the optimal area, and that's why it's called optimization. So we have some steps to follow in optimization. Identify what's being optimized, and that's going to be maximized or minimized. 2 is draw So we'll see this. If we have 100 feet of fence, maybe we'll say, oh, well, let's make it 20 by 20 by 60, or use 20, 20, and 60. We're just guessing numbers, how to divide up this distance. And then we calculate area, and we guess new numbers and calculate a new area. And we want to find the domain, meaning what are the possible values we can use? What's the biggest and the smallest values we can use for the 100 feet? And then we generalize whatever number we're changing, whatever numbers we're changing. We're going to generalize the changing values with variables and make equations. Once we have an equation, we'll have 2 equations. Usually we'll have 2 equations. Then we're going to find absolute extrema. That's what we did in the beginning of the chapter, and we just do all these things to set it up and then find absolute extrema, and that requires the critical numbers and endpoints. Check to see where the maximum or minimum value is for whatever is trying to be optimized, what we're trying to optimize. So let's look at the fence problem. Step 1, what is being optimized? We want to have the maximum area. Let's draw a picture. Here's a wall. Let's put the fence against the wall. We only have 3 sides of fence, and then the wall it doesn't require any fencing there. And so now we can just guess some numbers. 20, 20, 60. That's using up 100 feet of fence, and we get an area of 1,200. Is that the maximum area? We don't know, so let's draw another picture. And we could have 10, 10, and 80, and now we have an area of 800. Maybe that is the maximum area. Let's guess again. And we have 30, 30, and 40. We have 1,200, but there's another way to get an area of 1,200. And try one more. Here we have 40, 40, 20. We'll go back down to 800 for the area. So let's look at if we have the width, length, area. So let's call this the width. And here we had a 10 by 80. And we had 800. As we increase the width to 20, 20 by 60, we have 1200. And here we have 30 by 40, 1200. And now we go to 40 by 20. And that took us back down to 800. So now we can see that is the maximum area going to be between 1200, well, above 1200, and is that going to occur somewhere with a width of 25 maybe? So that is step 2, and we also want to find the domain. So what's the biggest width we can have? If we look at the picture, we could make a width of 0, and then the fence would be 100 feet long, but the area would be 0. Or we could have a width of 50, and then the length would be 0. Both of those have 0 area. We're not going to consider them, but we can see that the width can go from 0 to 50. The length can go from 0 to 100. All right, and we go to step 3, which is to generalize. When we generalize, we make variables. So let's call, we can just call it, make this y and x. And then we can have a formula. The area is xy. And we have 3 variables in an equation, but we're only used to using 2 variables. So what we want to do is make another equation that can substitute here and eliminate a variable. We know that 2y plus x equals 100 because we're limited on the amount of fence that we can use. And if we have 2y plus x, that has to equal 100. This allows us to solve for x, and then we can substitute for x over here. In place of x, put 100 minus 2y, and now we have an equation with 2 variables, and we can do step 4, which is find the absolute maximum. So I distributed the y, and now let's do step 4, absolute max. Critical numbers, we need the derivative minus 4y, and we want to know when that equals 0. So a critical number is when the width is 25. We also have endpoints of 0 and 50 for the width, so now let's check, and we'll have y values and area. So we could have a y value. We know the critical number is 25, and we can have a 0 or a 50. When we draw, we can just use the formula. Let's look at this formula for area. We want to find the maximum area. If y is 0, we go 0 times 100. The area is 0. We have a 50. If you put 50 for y, now we get 100 minus 100 is 0 times 50. So that area is 0. And then we'll put in a 25. So we have 100 minus 2 times 25 times 25. Here's 50, and we have 100 minus 50 is 50 times 25, and 5 times 25, 125. So we have a maximum area of 1250, and this is supported by what we found when we tried some numbers. We saw that the maximum was around 1200, and this fits in with what we found so far. And we just need to find the dimensions. The question asked for the dimensions, so we know it's going to be 25 width. Let's say 25 foot width, and that would give us 50 in length. Okay, you should try this on your own. Let me just write down what's happening here. We have step 1 you can do on your own. Step 2, I'm just going to help you visualize what is being described. We have a rectangular piece of cardboard, and then if we cut out the corners, it would allow you to fold the sides. So if we cut the corners and we folded, then we would have the base right here and a box going up like this, because we folded up the corners. Alright, so pause the video and try this problem. Find the height of the box that maximizes volume. So what are we trying to maximize? We want to maximize volume. So we're going to choose squares to cut from the corners. And if we know that that's 3 feet and that's 4 feet, let's just guess a number to cut from the sides, like 1. We cut out 1 foot squares from each corner. That means that when we fold it up, the height is 1. And after we cut out 1 and 1 from 4, then this leftover is a 2. And here we cut a 1 and a 1 from a 3, and we're left with a 1. So this is 2 by 1. So we'll draw that again. We have 2 by 1 by 1, and the volume would be 2. 2 times 1 times 1. So let's try that again with a different size square. We have 3 by 4 here, cut out a square. What if we cut out 1/2 of a foot on each square? We started with 3 feet, but we cut out 1/2 and 1/2, so we cut out 1 foot. That leaves 2 feet left. Here we started with 4 feet, and we cut out a total of 1 foot, and what's left would be 3 feet. So when we draw the box, we have 3 by 2 by 0.5. And that volume is 3 times 2 times 0.5 is 3. That made a larger volume by cutting out a 1/2 foot square instead of a 1 foot square. And then let's think of how big could the square be. If we only have 3 feet, the biggest we can cut is a 1.5 by 1.5, and then we'd have a 0 volume. So the largest value that we can cut out is 1.5, and the smallest value would be 0. Either way, we have a 0 volume. So let's keep track of what we found. If we cut out a side length of 1, the volume is 2. If we cut out a side length of 1/2, the volume is 3. And that was all step 2. Let's look at step 3. We want to use variables and an equation. So if we have this, we're choosing sizes of the square. So let's call that x. X represents any possible value we're going to cut out. When we fold it up, we know that the height is x, and then this started out as a 4, but we cut out 2 x's. So this is 4 minus 2x. And this started as a 3, but we cut out 2 x's, so that's 3 minus 2x. So that now we can write a formula for the volume depending on x, and the volume will be 4 minus 2x, 3 minus 2x, times x. And we go on to step 4, which is find the absolute maximum. And we're just going to expand that, so we won't have to use the product rule. We can just use the power rule for the variable. So when we multiply these two binomials, we have when you multiply all that out, we get that. If we combine and distribute, we'll have 4x cubed. This will be negative 14x squared. It's squared because we're distributing. And then plus 12x. X times 12. All right. Let's find the critical numbers. That requires the derivative. So we'll have 12x squared minus 28x plus 12. Do the power rule on each of those. We need to know when that equals 0. Here we can divide everything by 4. 0 divided by 4 is 0. 3x squared minus 7x plus 3. And we can just use the quadratic formula. We end up with x equals 0.5657 approximately. X is approximately 1.7676. But we found that the largest value of x is half of 3. The largest we can cut out is 1.5. So that helps us be aware that we can't use that. That's too big to cut out, but we can cut out a 0.5657. So now we check. We have values of x and the volume. The smallest value of x is 0. The largest value is 1.5. The critical number is 0.5657. We have a formula for volume. Here's one that we can use. If you put in a 0, we have a 0 volume. We already know that if you put in a 1.5, it cuts there's no width. It's two-dimensional and have a volume of 0. But if we put this into this, we have 3.032 as the maximum volume, and that agrees with numbers that we were finding here when we were guessing the side length. We can see that it's reasonable to have a volume of 3.032. So there's the maximum volume, and then we have and we found when we drew the picture, we saw that this side length of the square that we remove is the same as the height. So the question could be, what size square should you cut out? Here it was, how high, what will the height of the box be? But they are the same length. So we were able to find the height of the box that has the maximum volume. And we will stop there.